1 was equal to 2, and the corresponding eigenvector, 1, -1. Right? Second eigenvalue was 5, and eigenvector corresponding to that, we got 2, 1. All right. So we did that work previous to knowing why we needed to. But if we put that together, knowing the superposition principle that I pointed out to you on in section 5.1, I do know some solutions now, and that's what they talk about in the book, why this always works, that C1 x1 bar plus C2 x2 bar is a solution. And what we found is that we search for the form x1 in the form of v1 e to the lambda 1t plus C2 v2 bar e to the lambda 2t. All right. So this would be C1, and the vector v1 is 1, -1. Lambda 1 was 2, so this gives us e to the 2t plus C2, and the second eigenvector 2, 1, e to the lambda 2t, that was 5t. All right, so this would be a general solution of that first system that we looked at, that example. All right, a little bit further steps. If I push this constant or this scalar value through there, I can think of this as C1 1 times e to the 2t, so that would be e to the 2t negative e to the 2t plus C2 2e to the 5t and 1e to the 5t. All right, so I'm just unpacking this dense vector form of our solution. So we can think of it as x bar equals x1, x2 equals, and multiplying that scalar, it's C1 e to the 2t plus C2, 2C2 e to the 5t. And this one is the bottom, negative C1 e to the 2t plus C2 e to the 5t. All right. So in other words, unpacking that this vector format for these vector functions, these are the two solutions that we were hunting for x1. Not in bar, because not the vector value, but just a single valued function x1 of t and x2 of t. And they look a lot like the form that we found before, e to the rt, e to the rt, where these are solutions to a different characteristic polynomial characteristic equation. Okay, according to the eigenvectors or eigenvalues of the matrix P. Okay.
Solve 10 problems at once now.
Right. Basically, you're just solving 2 or 3 or whatever, however many differential equations at once, where they are interrelated because the dependent variables could appear in multiple equations. x1 prime equals x2 minus x1, whatever, and x2 prime, they could all involve each other, like those tanks. Okay? So this is a method similar to the single homogeneous linear DEs that we did. With with constant coefficients. Okay? But there's a lot of matrix notation, and instead of the characteristic polynomial plugging back into this higher order equation and getting a polynomial in R, we find the characteristic equation involves lambda, which is the eigenvalue of the coefficient matrix. Okay? All right. Now, I have a section here titled Complex Eigenvalues, and you know what? We're going to skip that today, because I don't want to start it with 20 minutes left. Okay? All right. So, we're still in 5.2. We'll finish. Give me more time to think about it, too. We will consider what happens in the case where we get complex eigenvalues. You can also have complex value eigenvectors, and that's when it gets fun. Okay, so we're going to do that. We're going to do that next. Oops, we're going to do that next time. We'll talk about it. So we're obviously, in case you have not noticed, we are behind where we're supposed to be. Okay, with all this material. Okay, I don't know how I can talk faster or give you more, whatever, but we are a little bit behind, so we're going to have to retool that a little bit. We'll talk about, I'll be up front with you. We may have to cut out. I think I've already planned. We're going to cut out like 5.4 or whatever, but we're going to get to where we get to. I don't want to just shove 8 more sections down into here before the final. Okay?
Yeah,
Appreciate that.
All right. There should be some semblance of understanding what we're doing. All right. One thing I do have for you, and we could work on this for 10 minutes. Let's work on this for 10 or 12 minutes. Some practice, at least writing systems writing a system in matrix form. Okay. Verifying that given solutions to a system are linearly independent. Number 3, you actually are looking at solving it, kind of like what we did here. There we are.